see is just the final value. So what you'll see if you put in, minus 3 is you'll see, in this case, minus 3 amps. Minus 2 amps. Okay, 0 amps, and so forth, right? So what you get. So is that true that it's R over L? Yeah, let's see. So V, I. So all you see is this kind of thing going on, right? So that's what you'll get in this case with this inductor. Yep. Did I mess up? What do you mean? Why? No way. Did I flip it over the first time? Oh, that's dumb. Well, this is a proof right here. This is my proof. We did it from scratch.
Remember I told you that because I'm sure you meant a mistake?
Yeah. Oh, yeah. Okay.
Yeah, that first time was wrong.
Well, there you go.
This is right.
Yeah, this is the proof, right? You happy with this right here? Okay. There you go. I mean, that's our proof that it's supposed to be L over R. All right. So we're happy with this, though, right? Like, basically, if you took an inductor and you did this, you get this characteristic, right? Okay. So does this mean that the IV characteristic of an inductor is shaped like a resistor's? Yes? No? What's the slope coming from? Exactly, yeah. Yep, exactly. So what you're seeing here is basically the resistor, okay? If we change resistors, we put a different circuit, instead of a resistor, what are we going to see here? Different IV characteristic, right? So someone was asking me, what's the IV characteristic, basically, of an inductor or a capacitor? And the answer is they don't really have an IV characteristic. What do they have? They have like an IDV characteristic, right? Or DIV characteristic, right? So it's not really the key, right? Is that if you apply a voltage directly to an inductor, the current's going to change over time, right? So the key basically is that inductors and capacitors do not have IV characteristics, and what they instead have is these differential things, right? Okay. So that's just a way to think carefully and critically about what would happen if we actually looked at one of these in the lab. So I'm kind of curious. So if we go back to the capacitor one, let's see what you guys said. It'll let me go back. Yeah. Oh, there's an anonymous question? Sweet. All right. Well. See if it'll let me open the database. Oh, hello. Okay. Well, I guess you guys don't really care if you see what answers people are picking. Here's the 19th. This is fun, right? Okay. I don't know if this is worth our time. Yeah, whatever. Okay. What is it with the capacitor? There might be. Up here? Oh, there was? Oh, well, there you go. Thanks, guys. All right. Aha. Oh, there we go. So it wasn't my fault that I put in horizontal. So on this one, right, the capacitor one, what's it going to be? So if you want to think about it this way, right, if we have this capacitor case, what's it going to do in time? Okay. It's going to decay, right? Okay, so it'll decay down. How long will it take? What's our time constant in the capacitor case? Yeah, that one we know. Okay. What's RC in this case? 1 nanosecond. Are you that fast? Not. Yep. All right. So what are you going to see on here if you measure the IV characteristic of a capacitor? So it'll be this one. Horizontal line, I equals 0. Because in the time it takes you to measure, the current that will appear briefly goes away. Okay? So there we go. Sorry for the confusion on the inductor guy there. Okay, so has everybody got this? Does it make sense? Now, if you applied a current source to a capacitor, what would you see? What would the voltage do? It would just grow, grow, and grow, right? So if you had access to some kind of a current source that could keep driving current forever, you would be able to, in very short order, pump just an insane amount of energy into a capacitor. So luckily for us, current sources are not ideal, and if you try and shove that much voltage or provide that much power out of them, they won't work, and they'll break down. They'll stop acting like current sources. So yeah. OK. So onward to stuff we've been discussing with phasors. OK. So before, right, we were talking about this notion that we like using capacitors for a few reasons. One is they're very useful for storing energy, right? We've talked about DC sources and how we can kind of store charge in them and they have energy in them. We can kind of look at how long it takes for these charges to come up. They're useful for filtering. So we haven't talked about that a lot, and that's what we're going to talk about more today. And they're also useful for modeling these parasitic capacitances. So this is the case where, for example, the gate delay thing I was talking about before, where in a circuit, right, you can model the time it takes for a gate to respond by capacitances. So suppose we want to find the voltage across a capacitor here, and the new thing here is that we have some sinusoidal source. What we'll see, as we said last time, is that the homogeneous solution is really easy, and that because the source, right, whenever you're doing the homogeneous solution, you toss out the source. You can go through and find the particular solution the usual way, right, where you basically make up a guess. You decide it looks like a weighted sum of sines and cosines, and trying to find coefficients that cancel. But the problem is, if you actually go through and do it, it's terrible. As you guys remember, there's the stopover. So there's sort of like these are like the two methods side by side that we're going to talk about. So the first is if we go through and do it the naive way, right? We make up a guess for what V should look like, and that happens to be the right guess, right? So there's already kind of a hard step, which is finding the right guess. You'd plug it into the ODE. You'd solve for A and phi, and that would be hard. And eventually, you would get your particular solution, right? So that's kind of like the way that we haven't done and we won't do. And I didn't give you guys the homework to do it because it's annoying. The other way, which is the thing I talked about in depth last time, was the idea that we consider a different problem entirely, where now, instead of looking at the problem that we're actually being asked, how does it respond to a cosine, we look at how does it respond to a complex exponential. In other words, the sum of a cosine and a complex, and the square root of -1 times a sine. So if you do this, you can plug in a particular, your guess is this. This has to be a nice guess. You plug it in. When you do this, right, whenever you're doing any of these circuits, what you'll always be able to do is divide by your original signal. So once you do that, time is completely gone. You end up with some equation, which will be in where you want to find K1, because that's the thing, right? When you have a particular solution, you make up a guess, and you find the constant. And then, as we said and talked about in some depth, the real part of this particular solution will basically give you the response to a cosine. So we'll talk about it, like kind of go through it once more, but much faster than last time. So basically, again, homogeneous solution, same as it ever is. E times minus t over tau. So then we pick a particular solution, this guy. So this is for the complex exponential case. So at this point, we've already done the replacing with the new source. So we plug in this complex exponential, and we basically all you do